Now in the S1, can you replace the I with M?
That's our condition. So now we can do this. So let's item. And then they usually allow me to do height. And similarly for all others, and then the anti-symmetry of this. Oh, Christian, sometime next week, maybe we can meet just to discuss going on the Alien project.
Yeah.
Okay.
Okay. I'm hoping for this weekend. I have some plans over the weekend.
Yeah, like just to catch up what we just talk about it.
Okay. I probably did see the kind
That's the stuff, yeah. Don't think about working on this. Okay, here, 1, 2, 3, yes.
What day works best?
How about Monday, Wednesday, Friday? Yeah, let's say. I have office hours from 3 to 4.
Okay.
Not many are showing up, so 3 to 4, let's say. Otherwise, 4, I'm sure.
Yeah.
I think it's also okay. Okay, I think all of us are here. All sets. Hello, guys. So, how is the homework going? Have you guys started by any chance, or is it useful whatever we did? Okay, so
Yeah, as usual.
by the end of today, we'll have more. So this is homework. One is due. And submit on D12 just so that it's all uniform. 1.1. Friday. So we are trying to work on index notation. This is basically so that we can work with vector algebra involving gradient operator. That's the goal. And so let's remind what we were doing. Index notation to work with vector algebra. And the idea is, instead of talking about the vector A, this is not strictly equal. So you say AI. So these are components of vector A. Components of vector A. Since they are components, so that's A1, A2, A3, together they have all the information about the vector A itself, but we should remember that it is the vector, and of course it is assumed that these are in terms of three orthogonal unit vectors. So a lot of, in that notation, there's a lot of implicit assumptions involved. But with that idea, we said that we can have a dot product written in terms of what we call a Kronecker delta. So whenever we have a dot product, it's good to think of this as AI, with the implicit idea that whenever the index repeats, there is a summation. You had imagined a summation over I there. So it is I running from 1 to 3. And we can also write this as I, that's a Kronecker delta, and speech. We introduce the idea of a Kronecker delta, which is a special, in a sense, matrix or tensor of rank 2, which is equal to 1 whenever I is equal to j, otherwise it is 0. So that's your P. And if you have a cross product, so this is a vector now, so it's ith component, so that this is the ith component of the vector representing A cross B. That's given in terms of Levi-Civita symbol, I, J, K, A, J, E, K. Okay. And this is what we, last time we introduced Levi-Civita symbol. It's a completely antisymmetric tensor of rank 3. It's either 1, -1, or a 0. And there are rules associated with it. If it is cyclic form, it is positive 1. If it is a countercyclic form, the indices appear countercyclic, or if they represent a countercycle, if you want, in terms of 1, 2, and 3, then it is -1. Otherwise, it is 0. Okay, so that's an idea. And we also introduced some identities. A couple of identities that comes out useful is, let's say, IJK, and this is IMN. Right? So now I is summed over. Sometimes it is K, sometimes it's J. In this case, it is I is summed over because it repeats, and this is equal to whatever remains, Jm, Kn minus of Jn, Kn. That's the identity that is useful in what we will be doing. So these are the three things you want to take home from whatever we did last time. Today, we want to use this for working with some examples. So that's your summary of what we did last time. Let's do some examples. So let's say we have basically combining these two. Example, the simplest could be That is A dotted with B crossed with C. I don't have to put the brackets because there is no other way other than first taking the cross, not the dot. You cannot take the dot product first because if you take the dot product, you get a scalar. Scalar cannot go with a vector, so there has to be only one place you can put that. First, you have to operate the crossover. That's a dot product. Notice how we proceed. First, I pretend that this is a single vector. So this is AI times. I can introduce the Kronecker delta if I want to, but otherwise I can simply say this is B crossed with C and I. That's how a dot product is understood in indices. And next step, I write the idea that this is given in terms of Levi-Civita symbol. So that's the I, J, K, J, C, K. And notice these are numbers, these are 1, 2, 3, and I haven't told you what this A, B, and C are. So we should be careful while moving A and B across to each other. For example, we can ask, is A times B always equal to B times A? Is it always equal? Can you think of examples when A times B is not equal to B times A? If they're matrices, that's not. Otherwise, any other examples? That's correct. Matrices are classic examples where A times B is not equal to B times A. Right? So, and sometimes we will have this way, especially in quantum mechanics, A times B, but we are in electrodynamics here, and even there you will see this situation. So, can you think of any other place where what would you associate A and B with, so that you can actually do this replacement? And I did say they are vectors actually. So, but we will be working with vectors. But since these are scalars, there is a classic example. Let us say that A is derivative, and this is a function f which is having a function of x. Now, if you notice, this is not the same as this. Right? So even if you have operations, gradient operator or derivative operations, then it doesn't work. And in this course, we'll be working a lot with the gradient operator. And that's the whole idea, that we will be working with vector identities with gradient operator, and we have to be careful not to move things around each other. So we should just be careful. So that's the point. So keep that in mind. As of now, I haven't said anything about ABC, so we'll just make sure that we don't move ABC around, okay? Unless it's told clearly that these are actually numbers, then we can move things around. But here, this is surely these are numbers, right? This is either 1 or a 0. I can move things even if it was a matrix or if it was a derivative operator, that will surely move through. So I can always move this I, J, K, A, I, J, C, K. Right. So that's good. But so this is all you have. But once I reach here, I can play around with it, and since I have epsilon I, j, k, I can move this to be. I can also think of this as k move things around, right? So move k to the front, and if I do this twice, I don't lose anything. So this is the same as epsilon k I, j, and AI J times C of K. So I use the property of Levi-Civita, saying that if I swap K and J, I gain a sign. But then if I swap K and I again, I gain a sign again, so I don't lose any sign there. But now I can interpret this to be a cross product. So this is A cross B K of C of K, which is nothing but A cross B dotted with C. Which is a standard vector identity. You might be aware of it before, but we just verified it using our index notation. Right. And so this is usually remembered as if you have a dot and a cross, you can actually move the dot and the cross, and that remains the same. That's, again, with if you have all vectors. So what about if you have a gradient operator? So now let's introduce a gradient operator. So the same thing. Let's first introduce what is called a gradient operator, just to give you a feel for. And let me say this is, first of all, what is a gradient operator? We will try to give meaning to this operator itself, independent of which coordinate system we are working in. But as usual, in rectangular coordinates, that is, it's not very useful to work in rectangular coordinates. But we'll try to resist this usage as much as possible. This is what a gradient operator is. What's the meaning of a gradient operator? Let's say, suppose I were to apply this on gradient of some function f of x. This is think of a temperature, right? It's a scalar field, temperature everywhere, and I operate gradient of a function. What is the meaning you can associate with it? Normal to the surface. That's very good. So the moment you have a function, you want to interpret this as gradient of f of x minus a constant. I can always do that, right? So because gradient of a constant is 0, derivative of a constant is 0. And now you interpret, what does it mean to say that a scalar function is a constant? So in this room, at every point, you have a temperature associated with every point. And then you ask, give me all those points in this room which has exactly the same temperature. And if it is a continuous function, that will form a continuous surface. And once you have a surface, this gradient is perpendicular to that surface. So the interpretation is that this is equal to normal to the surface f of x equal to a constant.
I'm sorry, Professor. What did you write? Gradient f of x minus what?
Gradient, constant.
Okay, just making sure. Thank you.
Oh, yeah. Constant. So when I write small, it's not very readable. And your audio was not on this system. Or is that not right?
It's probably my fault.
No, we should be hearing everything on the classroom audio, right? So.
Oh, yeah, I'm hearing your audio perfectly. I'm just trying to keep up with your writing. You write faster than me.
Oh, well. Oh, yeah. Try this again. Riley, can I say something?
Yeah. Can you hear me now?
Yeah, we can hear you. Yeah.
Okay.
Gordon, you have the. I think that. Yeah, it is coming out of the laptop, but I think. I can just once switch it off and then.
I'm sorry, I didn't mean to derail your lecture.
Yeah. Try once more, Riley.
Can you hear me now?
Yes, now it's good.
All right, sorry, I didn't mean to derail your lecture.
No. So this is important, right? More than half of you guys are. So, okay. So I meant to say, gradient of the function is the same as saying gradient of the function minus a constant, and then you say function minus a constant defines a surface in the sense f of x is equal to a constant. Right? Look for all those points in this room where the function is a constant if it's a three-dimensional space, and that once you have the surface, it is perpendicular to that. So example, right? So it's best to see this as an example. So example is think of a surface that's a sphere. Right? So what's the equation of a sphere? That's x squared plus y squared plus z squared is equal to r squared. So that's a sphere. Write this as a f of x minus constant. So this is minus r squared. Right? So this is your f of x. So I can ask. So this is my equation. So let me define my f of x to be x squared plus y squared plus z squared. Right, that's the equation of some equation, some function there. And then let's ask what is gradient of f of x. So this is I hat times derivative with respect to the function plus j hat derivative with respect to y. Okay. Derivative with respect to x, it only hits the x, so it is 2 times x. So it is 2 times x, and the I hat direction plus 2 times y, and the j hat direction plus 2 times z, and the k hat direction. But that's nothing but 2 times vector r. Look at this as a surface of a sphere. When you look at this as a surface of the sphere, like there's a circle, but this represents a sphere, and the center is here, and this gradient at every point is in the direction perpendicular to that surface, which is, if it's a sphere, it is outward from the, or the radial direction, if you want, right? So that's 2 times r. So that's a clarification of, or an insight of what a gradient operator is. We don't even have to do all this always. Whenever there is a gradient, if you know the surface, imagine it to be the normal to that surface. That's what we want to keep in mind. And we'll see the gradient operator a lot. We want to reduce our algebra as much as possible and be able to visualize what that gradient operator is. That is one of our goals of this first couple of weeks of vector algebra. So let's, once you have that gradient operator in our mind, let's do question. No. So let's try to work with gradient operator. So let's say A crossed A dot with del crossed with B. Or should I? No. Let's delay this a minute. Okay, so I want to do another example first. build on this. So, yeah, let's wait for a few before we go with the gradient operator. Let's do a simpler example without the gradient operator. Let's do A cross B cross C. Is this a vector or a scalar? Straightforward question.
It's a vector.
As a vector, right? It's, A, B, C are vectors, the cross product of a cross product, it's a vector. So I would be interested in the ith component of this. So that's the ith component. So it will have 3 components. So this will be epsilon I j k times aj and b cross c. Okay. This is do this 2 times now. Aj epsilon k m n e m c n. There are 2 epsilons showing up. We already know how to make this work. So this is m and k. Notice I moved my k twice. Right. Whenever I swap it 2 times, I get a plus 1. So this is a j d m c n. Again, I've moved my epsilon across a, even if it is an operator, that will work fine. This is delta im delta jn minus delta in delta jm. M, N, and then I start collapsing things, contracting m's. I get aj, bi, cj minus of aj, bj, ci. If I assume that A, B, C are not operators, if A, I, B, I, C, I commute, which is not the case always. In fact, even here in quantum mechanics, surely not, but even here it's not, because there will be gradient operators. But if it is true, then I can move things around. So I can move C around. So this is, I would say this is B, I, and then AJ, CJ minus AJ. So now AJ, BJ is nothing but dot product, right? I'm rebuilding my vector structure. Right. So this is also a dot product. So you would say this is the free index and a dot product, which is dummy index, minus, so suppose I move C this side, right? So this is usually written as cap. So I've been very free with moving things around here, and you will remember this as back cap rule, right? That's all. But we don't want to do this, right? We don't want to be commuting often. That won't be the case. And then we are left with a small trouble here. So think of this. So we have AJ, BI, and CJ, right? That's the quantity that is coming up here. That is a contraction between the 2. Correct? So we will often write this in a mixed notation. B is free. So the vector nature of this quantity is from B. And this is a dot product between A and C. But it's kind of a funny thing because it has to go through that. So as a notation, that is understood that A and C are dot product. It's a contraction. But if they are operators, you cannot do any better. So we will often use this as our notation. So there is dot product between A and C. B is a vector. Okay? We cannot, if A cannot go through this, we cannot do anything better. Sometimes I will also use this, but it's not a very convenient one. So this is a dot product between, so this means that dot product between A and C, and B is the actual vector. Sometimes in certain books, you will see this written as there is a dot product, but dot product not with B. So you will put a bracket around B, and then it is dotted with C. Right? This is dotted with C. This bracket means that it is dotted with C. I will typically use this notation or this notation. Right? So this will be the most convenient one. There is nothing you can do about it. You have to live with it, unless often it will be the case that some part of the vector can be moved. So C can be moved around, but A cannot be moved around. Then we can move things around a little bit. Okay, so that's our A cross B cross C. But now let's do immediately an example using gradient, where it's relatively simpler one. So this is gradient crossed with gradient crossed with A. Okay. And we'll come back to some examples with vectors along. So your homework mostly involves problems like this. Like you will have two of this, and you have to basically go around doing it. Don't do the explicit vectors. Trying to do it that way, that is too long. And usually, if you get used to this, idea is that you should, once you get experienced enough, you should be able to finish this in 3 steps, 3 or 4 steps. I wrote a lot of steps, but you can jump around, and typically you can finish this in 2 or maximum 4 steps in principle. So how does this go about? Same idea again. This is epsilon. Again, this is the ith component. That's ith component. So it's I, j, k. This is the jth component of the gradient operator. And then again, this is, let me write it explicitly. Can jump. But since it is the first few examples, let's do it in a few steps. Right. This is the first cross product replaced with Levi-Civita symbol, and the second cross product is epsilon k mn. Notice why I'm writing mn, because I've already used up my I and j. So I cannot use the same indices as dummy index more than 1. I should also point out that in an equation with lots of indices, for example, this particular equation, an index will never appear more than twice. If it appears more than twice as a, like for example, that was not intentional, that's a mistake, right? That was not intentional, I really made a mistake, even though I was just explaining that this is m. If m appears more than 2 times, you most probably, or for sure, if you're using index notation, you've made a mistake. It either appears once an index or it appears twice, never thrice. If it appears twice, our notations are not working, so you have to go back and change your notations altogether. But in index notation, it never occurs more than twice, and it will balance all the time. The free index on the left is only I, so there will be only one free index on the right, so they balance each other on left and right, the free index. The repeated index doesn't mean much, so there can be as many as possible, but only twice for each. Okay, so now again you can think of k going to the right, and this is delta im delta j n minus delta I n delta j m times this time gradient do the contractions. Delta im means that wherever I see m, I can replace it with I, right? And I can contract them. So wherever I see an m, I can replace it with I. So this is j, m gets replaced with I, and n gets replaced with j. Same as what is happening here, except that there is a gradient operator, and I told that until here this will be the same, but now there will be some changes beyond that. Minus, this is j, and m gets replaced with j, and n gets replaced with I. Now, here I is the free index. Now notice, I cannot move the I to the right because there is a derivative operator acting on something is not the same as something with a derivative operator on the right. But then, can I move it to the left? So we can ask the question. So this raises the question as to what if, is it possible to move to the left? So is j times I the same as question mark, same as I times j? In general, they are not. But in this case, is it? What does this mean? Like, what's the difference between these two?
Is the end result the same? It's just how you get to the end result that's different?
No, I'm asking the question, is this the same? Like, notice that what is this? Okay, del j of del I of, let's say there is an operator, it acts on a function, right? It has to act on something. Is that clear? Now, is this a tensor or a scalar or a what is this? How many free indices on this?
2.
2, correct? That's 2. So this is a tensor of rank 2. So there are 9 components to this, correct? So let's call this, just to give it a name, ji. Okay. Now on the right hand side, I build another one. So let's say del I, del j times f, and I say this is mij. 2 different quantities. That is, this is ji and that's ij. But the question is it the same or not? So let's look for components. So let's ask what is 1, 1. 1, 1 is d by dx of d by dx of f, right? And what is m11 here? d by dx of f. Oh, that seems to be the same, right? But what about other terms? What about 1, 2? This is d by dx, d by dy of f. What about m12 in this case? Oh, did I say this correct? 1, 2. 1, 2 is d by dy of d by dx, right? m12, the way I remember it, is j first, right? So the derivative with respect to y and derivative with respect to x. Now on this side, it is d by dx of d by dy of f. Is these two the same? You take a function, you first take the derivative with respect to x, and then you take the derivative with respect to y, or you take the derivative with respect to y first, and then you take the derivative with respect to x. Is there any difference?
I don't think so.
Any other comments? No?
I think if any number survives both, then it'd be the same no matter what.
That's a correct statement. Very good. Right. So partial derivatives commute with each other, and that is true whenever you want it to be integrable. Like we've always worked with functions where this is true. If by any chance you have such a function, then you cannot integrate it. Then integration is not allowed in that. So we never work with, but very rarely we come across that function. It's not that we do not come across it at all. Most of the time, especially, yeah, this is like you all have taken conservative forces, right? 205, we have talked about conservative forces. If the force is not conservative, then it's a path-dependent quantity, right? So if you integrate about from point A to B, the curve, which curve you integrate it on, that matters. And that's an example in which case this doesn't work. So as far as you're working with conservative systems, that's all okay. And we will be in that scenario. So partial derivatives, this is symmetric. It doesn't matter whether you go from one to the other. Any questions on that? So with that idea in mind, we can actually move this. So this is actually J. Not always again. Okay. This is only when this is derivative and partial derivatives commute. That's what we have used in there. And this is now a dot product, right? So this is a dot product. So this is del, and this is the I. This is the free vector. So this is a free vector. So this is your gradient. Sorry, this is a dot product there. So you learned that take the divergence of the vector A, then take the gradient of whatever that comes about, and this is this del dotted with del. Often you write this as del square. The notation. This is called the Laplacian. This is called the Laplacian. You'll see this again in more standard places very soon, probably next week. That's another example where you see a double cross product, but this time with operators, the gradient operator showing up. And we will be dealing with this gradient operator a lot. So we will be working with identities like this. That's our focus. Another example, which will be useful for your homework. Let me see what your homework is. So this was exactly what I was going to do. Yeah, also this. So there is this is A crossed with B and charted with, so that's a vector, and this is also a vector. Right? Two vectors, and you can take a dot product between them. First one, there's a dot product, so I can say this is the ith component of A cross B and the ith component of C cross B. That should be clear. So that's a dot product, and this is equal to epsilon I j k A j dk, and this is epsilon I cannot use j and k now, I have to use m and n, cm n. This to have this identity again, so this is this time. Forget the I because it's repeated, j, k, m, and n, right? So this is j, m, k, n, j going with m, k going with n, and then swap it. J going with n, k going with m. Now there are four quantities now, k, c, m, e, n. Start collapsing. The idea is that m gets replaced with j, n gets replaced with k. So this is a j, b, k, and m gets replaced with j, and d gets replaced with, n gets replaced with k. Minus a j, dk, c goes with k, and n which is the index of d goes with j. If these are not, or if all these components commute, only if that is the case, if the gradient operator, if the components commute, then you can move things around. So I can move the j around. This is aj, cj, dk, dk, and I can move d around. So this is aj, dj, and dk, ck. Only if they commute. Like if there was a gradient operator, it doesn't, like we did an example. Identify your dot products. These are dot products. These are dot products. That's dot product. And you see that this is A dotted with C, and B dotted with D. In this case, it flips, right? A goes with B, which you can see right away. So with a lot of experience, you can see through this right here, and you would say, oh, A goes with C, B goes with D, or swap it. A goes with D, and B goes with C. Any questions? So all this should help you with your homework a lot. Next week, we'll be pretty much dealing with the gradient operator. We'll talk about the properties of a gradient operator, which is what will be the main content of the, that's why we are working on this, so that we can easily work around with the gradient operator. And we'll try to make this coordinate independent very soon. Any questions? I'll put the camera on. Maybe the students instead of me, you guys thought. Yeah, they don't have that cameras.
I'm waving back. Trust me.
Good. So anything else? Any comments, questions, or in general, any?
So what would be like the physical interpretation or for a dot product with a vector in between? Is there any
Dot
sort of
product with a
interpretation?
vector in between. Oh, yeah. So let's do that. Yes, so I think I understand your question. So I think the question is, so what is the meaning of, let's say, A and B and C, correct? Let me write A on the side, back, right? So this is A here, B here, C, right? With this, correct? First, let's ask a simpler question, because it's the same thing except that they are operators. Right? What does this mean? It is the same thing except that they are operators. So what does that mean? Let's go back to cross product. Okay, so this is A crossed with B crossed C. Right? Ask the question: where is this vector? Whatever this vector is, this new vector that we call this M. M has to be perpendicular to A. There's no other choice because cross products are always perpendicular to both the vectors. So there is a vector A, let's say. So vector A is perpendicular to the plane. Now my vector M is in this plane for sure. Then I just need two vectors. If I want to write a vector in this plane, I need two vectors, right? It could be E1 and E2. I just need to get those two vectors, or for that matter, I don't even need an orthogonal set of vectors. I can also work with any two vectors, right? So I just need whatever M is. So let's say M is here. I want to write it in terms of two vectors. And that's what this cross product is. It is written as, what is the component along B? It is A dotted with C. This is a projection of this quantity along B. That's what this means. Projection of this vector along B. And minus of cap, so it is C of A dotted with B. Projection of this vector along C. So that's one way. In the cross product, that's what it means. Okay, does that help?
So they still, A and C will still turn to a scalar and it'll still be in the direction of B.
Yes. It's just that you cannot write that complex. I mean, as far as concept goes, it's the same. It's just that these are matrices, right? All the matrix properties still work. You have to take the product and all that. But if it's a derivative, for example, all that goes through, but you have to respect the fact that you don't go through it. Let's take a specific example, profitability. Let's see, like where this will come up is the gradient operator is, let's say, for example, you will come across this quantity. So I think A dotted with a gradient and then operating on B. How about this? I think this is a good point. So, but no, I want a dot. Right? I cannot think of it. Gradient. Let's say. So this is C. How about this? So this is dot. So I cannot take. It would have been convenient if I could write this as this. but I cannot write that because that would mean that I'm not operating. These two are not the same. So this means that this is acting on both, but this is the free vector is decided by the P. I'll try to come up with a better interpretation. Yeah, and I see your question, but I'm not able to come up with the right answer. Yeah, good question. Oh, actually, we need extra credits, right? I keep forgetting. Did I give an extra credit today? Yeah. Since I'm not able to do it, come up with an insight to see what is the interpretation of A with this dotted. Okay. An interpretation of A dotted with C in the direction of B. Is there a physical interpretation of this? Again, you're allowed to look up, remember everything, or give your thoughts, that's all. Or at least try to understand the question that's also the number. Yeah, I hope it is fine to ask questions which I don't have answers to immediately. But then it's a participation. Okay, thank you.
Thank you. Have a good weekend.
You too, really enjoy. See you guys.
Thank you.
Bye.